Very good evening, everyone. Can you guys see and hear me? Thank you, Arad, for confirming how you guys are doing. I know it was very long weekend, right? Oh, not weekend actually. What is it today? We met on Monday, right? Oh, yeah, my mistake. Yeah, it's a Friday, right? So yeah, it's still I think we met last on Monday, right? After that, today we are only meeting. Yeah. What about you guys? I know something was happening internally in the Reliable, so they have suggested me to cancel the previous class and start today with hashing. I think they are planning later to cover the revision class. So that's why, yeah, I was also very excited for the revision class, but now they are saying that they want to start with the hashing first and then later wants to go for the revision class. Then I told, okay, we can go for that as well. Okay. But yeah, we will definitely do the assignment questions. And in that assignment question, those 7 questions are very interesting. So we'll first definitely see those assignment questions, and then we will start a new topic today, which is hashing. It's a new data structure. So very excited for that as well. So yeah, so meanwhile, guys, I already told to you that if you guys have any queries, you can simply ask me on the LinkedIn group. I think in meanwhile, who was that? Ekta, yeah. So Ekta has shared some of the queries there, which I have already seen it, answered her. So in similar way, you guys can also do the same, and it would be great to help you guys. Yeah, we'll wait for some more minute, 1 or 2 more minutes, and then we will start our today's session. And I hope you guys have got, I think, longer time, right? Because it was Tuesday, then we have Wednesday, and then we have Thursday as well, right? So in that 3 days, and I think today's whole day. So I hope you guys have practiced lot, and anyone has tried to solve the assignment questions which was mentioned in the previous slide, previous class. Anyone tried? Yeah, I know you guys have done practice. Anyone tried? Okay. Oh, okay. So our others tried. Were you able to solve it, or still find anyone anytime difficulties? Can't. Okay, no problem. We'll see them today, and then we'll try to understand the logic as well. Yeah. More people are joining. Still confused over the previous class questions too. Yeah, I can understand. There would be some of the doubts. If you have any specific places, I can go through quickly. Otherwise, we have to wait for revision class to explain the whole part of it. But if you have any specific, you can ask it here or in as well in the LinkedIn. Anywhere you can ask that. If you have any specific places you're not able to understand the coding thing or not able to understand the logic of that. Yeah. So I was saying binary for me it was hard. But for me hard in coding. Hmm. See, what I understood well, I was trying to solve the binary questions. It was always, I have seen that we are using some data structure, or specifically in data structure, if we talk about, we are using stack or queue, a lot of places. And after that, after stack and queue, it's just the traversing part. Sometimes we are traversing is through the DFS. Sometimes we are doing traversing through the BFS part. So that's what mostly we are doing it here. Today's question also we'll try to do this. These follow the same strategy there as well. We'll use some data structure like stack and queue, and then we'll try to traverse the arrays. And then we have to do a little bit logic side as well. So these three things are there while solving the binary trees questions. Okay, okay, guys. So now let me share my screen. I think we have already spent 3 minutes, so let's start it. Are you guys able to see my screen? Thank you, thank you. Okay, so I already opened the, yeah. So these was the two problems, guys. Let me just little bit increase the size here. Yeah. So see, guys, they are saying that they have given us a binary tree. You can see it in here. The binary tree is here, right? And now they are saying us that we need to print the top view. Correct. So if we want to see this tree from the top side, like we are standing on one building and this tree is standing on the ground, and if you want to see the top view, so what are the nodes you will be able to see it? So you can see from the top, these would be the nodes which we are able to see it. So those nodes are 2, 1, 3, and 6. Correct, guys? So 2136. That's what they are asking. So if we have a tree and if we want to see it from the top side, so what are the nodes we were able to see it? We have already done the similar question where they were asking if we are going to see the tree from the right side. Yes, right view. So there we have thought there I told you that they are trying to ask at each level what are the last node. Correct. At each level what was the last node. In that way we have solved the right view question, but here they are asking about the top view. Correct. So let's come back to the question again. They are asking about the top view. So guys, let's draw this tree and let's understand how we will solve it. Let me open the OneNote here. Yeah. So let's draw this. Let's choose a pen here. Well, yeah. So now we have the pen here. So it is 1. Then we have 2, right? Then we have 3. What happened? Yeah. Then we have 3. Then we have 5. Then we have 6. And then we have 7 and 8. 7 and 8. Right. They're saying to us, guys, to print the or give us the nodes which are visible from the top view, right? And our output is 2, 1, 3, 6. Correct? I hope everyone understood the question. Question was very easy, right? So Likit is saying here root plus left till leftmost plus right till rightmost. So root plus left till leftmost. So Likit is saying let's start traversing onto the right left side till we got the leftmost. It means left leaf node, right? Leftmost means left leaf node. Okay, let's see that. So if we will start traversing from the root, which is 1, correct, guys? Everyone try to relate it, but look at this time say, so this is our root, right? And from the root, if we traverse to the left side, so this is our leftmost, which is 2, correct? And then what Likit is saying, then we have to go to the right side till we got the rightmost, correct? So now if we go to the right side, so we'll see the 6. That's also right. We'll get the 6 here. And then what we need to do next? We have to come back here to the 3 side here. No, 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 no. According to the logic Likit, see what will happen. We'll start from the left side and then we'll go to, then you're saying we have to go for the right side. Correct? So first we'll go for the left side, we'll get 2. That's fine. Answer is 2 here. Then we'll go for the right side. And for the 1, right side is 3. So now we have this big tree. Now we'll go again into the left side, right? That's how the logic will work. Left, right, left. Again we'll go to the left side. We'll get the 7, which is not our answer. So that logic will not work there. Correct? The only note seen from the top view. Because this example is in this example, just see that Vishal. These are the nodes which will be visible on the top side. So if you want to see this from the above, so just make this 3 and 6 like a horizontal. So you will be only be able to see 2, 1, 3, and 6 from the top. Just make like, okay, if I make like this 2, 1, 3, and 6. So these are the nodes, and then 5, and then 7, and then 8. So you will be only be able to see these nodes. Understood, Vishal? Okay. No, it's still rightmost until right is null. It's still rightmost until right is null. Okay, guys, we'll look into that logic also. Let's see one another logic, one another approach here, which is what we'll do, guys. Here, as you can see in the while we were talking about the questions as well, just create a vertical line at each nodes. So just create a vertical line as they have created. You can see, just create a vertical lines here. Like this, and give them like this, give these vertical lines some values. Give these vertical lines some values, like let's start from root. So for root, let's give it a 0, right? And whatever going into the left side, just do the -1 into that value. So right now it's 0, right? So for 2 it would be -1 here. Correct? For 3 it would be +1. For this one it would be +2. Correct, guys? So what we need to do at each line, we just need to check what are the first value which we are occurring. If we are creating a vertical line in each of these nodes, so just we need to see what are the first value which we are getting it while we are seeing the while we are drawing the vertical line into each of the nodes. Correct? You can see from the root node I drawn one vertical lines. Same for next node as well. All the nodes are coming into this verticals. Same for this one, same for this one. Correct? So once I draw this line, you just need to find it out what are the first values. What are the first values coming into that line would be our answer. And you can see there for the -1, first value is 2. For the 0, first value is 1. For the +1, the first value is 3. For the +2, the first value is 6. And that would be our top view, guys. That would be our top view. Did you guys understood? If we can draw one vertical line, then we can see whatever the first element is coming into that vertical line, that will be our answer. Correct, guys? And for that, what I'm saying, start our vertical line from the root. Start our vertical line from the root and make that vertical line value as a 0. If you are going into the left side, just increase the value as -1. And if you are going from that node, if you are going into the right side, just increase the value as +1. That's what you need to do. Correct? So see, guys, and after that, what you can do, you can take one map or object, anything. So see what we'll do, guys. We'll take first one cube. We'll take one cube. Okay. And while we are creating a node, we'll take now 3 values. One is the left, Second one is the right, and one more value. Four. We can say it as a vertical line. At which vertical line right now it exists? We can say we can take 4 line here: left, right, value, and vertical line. Correct? Or if you do not want, still that will work. If you do not want to keep while constructing a node, that will still work, because it's at the end it's an object, right? We can add it at any time. Correct? So now let's start from the first root. Let's start from the first root. So first root is this one, right? This is a root element. So first keep it into, before keep pushing into the queue, before pushing into the queue, just update the vertical line value of it, which is 0. For the root node, just update the vertical line value of this, which is 0, and then push it into the push it into the queue. Now 1 is here at the 0, and it will keep two things. Let me draw the proper. It will keep two things. So first thing is the vertical line value, and second one is the that node value, which is 1 here. So you can see this is 0, this is 1. Correct? And now let's create one object at this place. So at the 0th place, we got the 1. Correct? At the 0th place, we will got the 1. Correct? Now let's go for the left side, left, right, left child and right side. So for 1, left child is 2. For 1, left child is 2. So now whenever we are going into the, this is for 0. Now we are going for the, this is for root. This is for root, which was 1. Now we are going for the left child, which is 2. Correct? Our left child is 2. So for, because see, I told you, whenever we are going to the left side, we just need to subtract the value. We just need to subtract the value. So now what we'll do, before before going into the left side, what we need to do, we need to subtract this value. So right now for root, the value is 0. So for going into the left side, it would be -1. -1. And for the right child, which is 3, the value would be +1. So the node would look like this: +1, 3, -1, 2. And then insert it into here: -1, 2, and +1, 3. And now let's remove the root node from here, because we have already traversed the left and right side of root node, so we do not need it. Correct? Now let's go for the next element, which is -1, 2, right? The left child. So now we are going for the -1, 2. Right now our vertical line is at -1. So first we'll check, is the -1 exist in our object? No. So it means it's the first time -1 is coming. So now we will put the value here. First time -1, 2 is coming. So we'll keep the value at this place. Now we'll check for the left and right child. 2 does not have any left and right. So what we'll do? We will not do anything. We will not push anything in this queue. We'll just simply remove it. We'll simply remove this entry. Correct? Now we'll go for the +1. Now we'll take this one: +1, 3, +1, 3. So now you can see vertical line value is +1 right now. Correct? So now first we'll check in the object. Is +1 exist? No, +1 does not exist. So +1 and add the value there. So 3 is there. Correct? Now we have to go for the left and right child. So left child is 5. Left child is 5. So what I told you, whenever we are going to the left side, take the current vertical line value and subtract it. So for +1, it would be 0. Correct? And for the right child, which is 6, the value would be 2. Correct? So how will it look like? 2, 6, 0, 5. And that's what we will insert it here. And remove the +1, 3. After removing this, first we'll insert the left child 0, 5, and then we'll insert the 2, 6. Correct? Now guys, now see the important logic. Now 0, 5 will come out. Now 0, 5 will come out. Correct? This time in our object, we'll see 0 exists. Yes, we will not update the value of 0. We will not update the value of 0. And then we will traverse it again. Now the vertical line value is 0. Again, we'll check the left side, which is 7. Left side for 0 is, for the 5 is 7. So, and the vertical line value would be 1, sorry, -1. The vertical line value would be -1 because you can see vertical line value is 0. So for left side, always subtract it. For the right child, increase it. Now for the right child, it would be 8. Right child is 8. You can see for the 5, will increase this +1. So how will it will look like? It will look like this: -1, 7 +1, 8. Here we will insert it: -1, 7 +1, 8. And then we'll take out the 2, 6. Take the 2, 6. We'll again check. 2 exist? No, it does not exist. So 2, 6 first insert it here. Correct. And then again check left and right exist. No, it does not exist. Let's remove it. Now let's go for -1, 7. -1 exists. Yes, we'll not update it. -1, 7 any left and right? No, just remove it. Let's go for +1, 8, which is this one. +1 exists in the object. Yes, it exists. We'll not update it. 8, does the 8 has any childs? No, we'll remove it. Now our queue is empty. We'll come out of the loop. Understood, guys? So with the help of queue and the one more data structure map, we have done the code. Correct? So why we are using the map? Understood this vertical line concept? Yes. See, why we are using the map? With the map, we are just trying to track whenever a new vertical line is coming, do we have already that vertical line value or not? So you can see once first time 0 when first time 0 vertical line comes, we just kept the information here as a 1. Second time -1 vertical line comes, we kept the value as a 2. Third time +1, this third vertical line comes, we just kept the first value. You know that +1 vertical line came for 3 as well, came for 8 as well. Same, vertical line 0 came for √1 as well, came for 5 as well. But we just kept the first value. And that's what you can see. And that's what we are going to give us answer as well. We just need to sort it properly. And then we will be getting the 0, 1, 36. We just need to sort based on the queue. We just need to sort based on the keys. And once we will sort it, we will get our final answer as a 2, 1, 3, 6. And this queue, we are just simply using to traversing our element left, right, left, right. Everyone understood? Are we good with this question? Could you please? Oh, sure. So, Vishal, what we did, we got this binary tree, and what we did, we draw one vertical line. In our binary tree, we just started drawing one vertical line. Whatever nodes are coming in that vertical line, we will give them some value. We'll give them some value, and we are going to start our vertical line from the root, and that vertical line value would be 0. And whenever we are going into the left side of that vertical line, that would be -1. Like the just subtract -1 into that. And if we are going into the right side, just add +1 on that. That's what we did. So we started with our root. And we just taken two different data structure as well. One is our queue, and one we have taken map here, as map or object, whatever you want to say in the JavaScript. Correct. So we have taken two different data structures here. Queue we have taken just for traversing. Why we have taken queue? Just for traversing, because we are doing the BFS traversal here. That's why we are using the queue here. Correct. So we started with our root. So once we started with root, we just added one more key into that, which is vertical line value. For that node, we just added the vertical line value there. So because I already told you, we'll start with the root. So root vertical line value would be 0. So now we started with the root. Whatever coming into the left side, it will have vertical line value as a -1. Whatever node will come at the right side or right child, that will keep as a +1. Now these two childs will be inserted into a queue. Now again, we'll take first child. We'll do the same for that as well. If it has left child, we'll just do the -1 for the vertical line. If that child has a right side, we'll do the +1 for that. That's what the logic. At the end, we'll traverse everything, and in the map, we will only keep whatever the vertical line first time coming. Like first time -1 came, then 0 came, then +1 came, +2 came. Whatever the vertical line first time coming, with whatever value they are coming, those vertical lines, we'll store them in the map. And then at the end, once we have this map, we will sort this map based on the keys. So first -1 will come, because once we'll sort based on these keys, so -1 first will come. then 0 will come, then 1, then 2, and based on that answer will also come. So minus 1 will be pointing out to 2, 0 will be pointing out to 1, and 1 will be pointing out to 3, 2 will be pointing out to 6, and that would be our answer. 2, 1, 3, 6. Understood, Vishal? Now let's me. Everyone understood? Arad, Hariharan, Suraj, Joseph. You guys understood? Yeah. Let me show you the code now. Yeah. Now you can see they have taken the four fields here. This is dot data, left, right, and vertical lines. Even if you do not want it, you can still go with it without having the vertical line as well. Correct? Because it's an object, we can add anytime any value into that. But it's like, I think, good practice. They are keeping it into, like, they are showing you all the node has vertical lines. I think this is a good practice. Correct. So now you can see first we have taken q, then we are taking the map, then we are giving our root the default value of vertical line, because you can see first I'm inserting my root into the queue. So at that time I'm just providing the vertical line as a 0. So once I provided the root as root vertical line value as a 0, now just entering into the queue. So taking it out that root, taking it out the root value, then we are checking, is that value already exists in the map? If not, then set it. If that vertical line value is coming first time, then set it into the map. If not, if it's already exists, do not need to set it. That's what we are doing, right? In the each vertical line, we just need to check the first value, minus 2, 1, 3, 6. Whatever the next time those values are coming, we do not need to take them. So that's why this line is doing that part. It is only taking if the vertical line value first time it is coming. It will only set that one. Otherwise, you can see if we are going to the left side, we are going to the right side. If we are going to the left side, we are just subtracting our vertical line value. Whatever current vertical line value is, just subtract it for the left child. Same for the right child. If that has right child, just add it and then push it into the queue. And at the end, once we have traversed the root element, just shift it, remove it from the queue. So this is our looping part that's happening. And now after that, once we got our map, we are just converting into the array, and then we are sorting it based on the key we are sorting out. So array dot from will give us the array of the map. So like map could be converted into the array, and once you converted it, then we are simply sorting it, and we are sorting it based on the 0th index, which would be our key. I will show you. I will print out this array. You guys can see that. And at the end, we are just consoling it out our output. So let me show you. I think, yeah, I already checked it, so you can see it. But let me do it again. 1 minute. Let me run it. Problems tree top view. Yes, you can see this was coming earlier. Once we converted our map, look, let me print out the map also, so you guys can see the map, how the map looks like. It's an object only. If I just want to tell you, the map is simple object. Let me show you what happened. Oh, map doesn't exist. M. Map is defined with M only. Yeah, you can see this is the map. Simple like object, right? 0 is the key there, 1 is the value. It looks like this. Then we converted it into the array. So this looks like this: 0, 1, minus 1, comma 2, 1, comma 3, 2, comma 6. And who is converting it? This line, array dot from. And then we printed our second array. And after that, we are sorting it based on the 0th index. You can see after sorting, minus 1, comma 2 is coming first. Earlier it was coming here. Then 0, comma 1 is coming, 1, comma 3, 2, comma 6. And then at the end, we are just traversing it one more time on the final array. And then we are simply printing out the values here: 2, comma 1, comma 3, comma 6. And that was our output is. Understood, guys? Array.form will give array of values of map. So array.form will give us both things, key and value. It will give the pair of that. Okay, Likit? Why are we adding and subtracting? Why we are adding and subtracting, and which line? Add which line? Oh yeah, this one. Adding and subtracting. So, so just you remember when we are at the root, if you want to go to the left side, we have to subtract that vertical line. Then only we will get to know, right? And these all nodes are coming at -1 vertical line. And when we are going to the right side, we are going to do +1. Understood? That's why we are subtracting. Whenever we are going to left side, we are subtracting into the current vertical line value. And when we are going to the right side, we are adding it. Because based on that value only, we are able to understand that this is the next vertical line. And in that next vertical line, whatever the first node exists, we have to take it. Understood? We can either, it's for copying element. We can either start from left or right. Yes, we can go from anywhere. If you are going to the right side, we have to do +1 first, and then we can, if you are going to the left side, we can go for the -1, and all nodes will be traversed in this. Yes, all nodes will be traversed. Totally right. Understood, guys? Arad and Joseph, did you understood what I'm trying to say about the adding and subtracting the part? Yeah. So once more the coding part. Okay. Let me go again. So you guys can see. So first we have taken the queue, then we have taken the map. And why we are taking the map? Because the reason for taking a map is we are going to store our vertical line values with the node value. Correct? That's why we are taking our map. Then we are initializing our root with the vertical line value as a 0, because you can see our root is going to start with vertical line 0, and then whatever coming at the left side, that would be -1. Whatever coming on the right side, that would be +1. Then again 3's right side would be +1 again, 3's right side would be -1, and this will have everything happening on the vertical line values. Vertical line value is +1. So right now 3's vertical line value is +1. So for all of the right side of it, it would be vertical line +1. And all the left side of it, it would be vertical line -1. So that's what you can see. This same code is written here, line number 21 to 28. So before pushing our root into the queue, we are updating that particular node's vertical line value, which is vertical line -1, vertical line +1. So that particular thing, which is I'm explaining here, that's what happening in this line 21 to 28. And then this is one more line which is added here at the line number 20. What this line is doing, it is setting this map, because in this map we need to set our vertical line value with node. So this is vertical line value, this is node value. You see at the 0th vertical line, 1 is the first node, so that's why 1 is coming at the first. At the 0th vertical line, 5 is second node, but we do not need 5 as a second element in that vertical line. That's why we are putting this condition: if m dot has that vertical line, if map does not have vertical line, then only keep it. If map already have that vertical line, do not enter it. Do not go in, do not set a new or update the value of that vertical line. You can see 0 has already set the 1. So for 0, 5 will not be set. So that's why this line is written here, line number 20. Now, once we have already completed, and our map looks like this. Our map looks like this: 0, -1, +1, comma 2. Now we need to understand from which direction, we have from which direction our element, because you can see 2, 1, 3, 6. That should be our answer, because if, according to our output, we are looking from left side to the right side. So that's why what we did in our vertical line, in our map, we just sorted it out based on these key values. So sorting, it's very easy once we convert all of the things into array. So that's why into the next line you can see we converted our map into an array with the help of array methods, array.from. So once we converted it, now we got an array, and now we just simply use the array.sorting logic for sorting based on the first index or the left side value, which you can see as a vertical line. Once we sorted it out, so -1 will come first, then 0 will come, then +1, then 2. That's what you can see, -1 0, 1 0 1, 2. Then we got our final output 2136, and that's what we are able to see it here. This is our map, and this is our like converting that map into an array, and this is the sorted array. You can see -1 is coming first, then 0, then 1, 2. That's what I showed you there as well. And then at the last, we are printing out these values 2, 1, 3, 6. Understood, guys? Arad and Joseph, yeah, clear now? Sir, inside the loop, each time value should be shift from Q, right? Inside the loop, each time value should be shift. Yes, that's happening here. Yeah. Yeah, this line number 29. Every time we are shifting it out. Once we traverse that value, we are just shifting it out. Confused over the line number 20. Line number 20. This line. Okay, understood. Yeah. Everyone good, guys? Can we move into the next question? Yes. So next question is little bit difficult, guys. But like see, question is difficult and has been asked in bigger organizations as well, like in Amazon or might be in the Google as well. Not sure, but in Amazon I have seen it has been asked. So that's why it's little bit tough to understand. Not tough to understand, I would say. Little bit tough to understand the coding part, but I'm telling you, I will try my best to explain this that next question in easy way. Okay, and we'll try to understand in easy way. Okay, so let's see the next question, guys. And very interesting question actually. So now, guys, what they are saying for our next question, and just keep like your mind active so you can quickly catch whatever I'm saying. Okay. So what they're saying, they have given one integer n. Any integer could be, and then that integer will start. I think yeah. So they have given one integer n, and we need to return the number of structurally unique BSTs which have exactly n nodes of unique values from 1 to n. I know you guys might not be able to understand, but what they are saying, they will be giving us one number like n is equal to 2. What you need to do, you need to start from 1 to n. It means 1 to 2. Whatever number is coming between these two numbers, like between 1 and 2, only two numbers are coming, which is 1 and 2. Like if they are giving n, 3, then it will be 1 to n, which will be 1 to 3. It means 1, 2, 3. Same for n is equal to 4. So you need to, did you guys understood? I think you guys have understood what the meaning of 1 to n here. So, so what they are saying here, you need to construct a unique binary search tree with these numbers. And how many binary search tree uniquely you can create? How many binary search tree uniquely you can create with these numbers? Correct. So now so like if n is equal to 1, so it means your range is 1 to 1. It means you have only one number. Correct. Start from 1 and also 1. So it's only, you have only one number. So with 1, with the number 1, how many binary search tree you can create? Okay. Before that, what is the property of binary search tree? What is the property of binary search tree? The left side will be smaller than the root and right side would be greater than root. Correct? Greater or equal than root. Correct? That's the property. Left should be smaller than root. Yes? So that's the property. So see, if we have only one number, like which is 3, how many binary search tree we can create? Only one. Correct? So let me write it at this place. Let's write it. I'm writing number of nodes. And here I'm writing how many or BST. How many BST we can create. So if number of nodes are 1, how many BST we can create? Only 1. With this 1, we can't do anything, right? With this 3, we can't do anything. Agree, guys? Understood? With number 1, we can't do anything. Let's try for n is equal to 2. Let's try for n is equal to 2. Let's remove it. This is n is equal to 2, right? We already had here. So our range is 1 to 2, which has given us two numbers, 1, 2. So how many binary tree we can create with 1, 2? Just think about it. Anyone does not get the answer. That's why I'm saying just quickly run your mind. How many binary trees we can create with these two numbers? No, with these two numbers. These two numbers should be used. Every time these two numbers should be used. Arad, Hariharan. Every time these two numbers should be used. So yes, we can only create two binary trees. So first binary tree is if we consider 1 as our root. If we consider 1 as our root, so 1, 2. This would be a first binary tree. In the second scenario, if we consider 2 as our root, then 1 would come at the left side. Only these two we can create. Correct, guys? Only these two we can create. So that's why when we have number of nodes as 2, we are going to create the two binary trees. Let's go for quickly for n is equal to 3. Anyone wants to guess how many trees we can create for n is equal to 3? Vishal says 6. What about others? Okay, that's not easy actually. You need to construct it. So let's construct it, guys. So let's go for n is equal to 3, where our range is 1 to 3. It means our elements are 1, 2, 3. So see, guys, very easy way. Very easy way. Start trying. Take one each nodes here as a root. So let's first consider 1 as a root. So if we consider 1 as a root, so remaining element, let's look for remaining element here. On the right side and on the left side. Correct? So on the left side, we do not have anything. So just written the null here. Right? On the right side, we have 2, 3. 2, 3. Correct? Now this 2, 3, how many? Now this 2, 3 will make how many binary trees? This internally 2, 3 will make how many binary trees? I have already told you two numbers. If we have given two nodes, how many binary trees they can create? 2. Correct. So if we simply, so it would be 2, 3, and 3, 2. So if we combine everything here, so it will be look like this: 1 null 2, 3, and second would be 1 null 3, 2. So while considering 1 as a root, we can possibly get two binary trees, two binary search trees. Am I right, guys? While considering 1, while considering, yes, we will definitely use recursion, Likit, definitely. While considering 1 as our root, we can construct two binary search tree. Now let's consider 2 as our binary root. And let's use the same logic, guys. Let's look for left side, look for right side. So if we will look for left side, we will be getting 1. Let's look for right side. We will be getting 3. So with one number, how many binary trees we can get? With one number, how many binary trees we can get? Only one. Only one. So that's why while considering 2 as a root, we can only construct one binary search tree. You can see this is the binary search tree we can create finally. Correct? Now let's consider 3 as a root. Now let's consider 3 as a root. So now again do the same thing for 3. All the right side of it will be null because there is nothing. On the all the left side would be 1, 2. Now again for 1, 2 there would be two possibilities, which is 1, 2, 2, 1. So the final tree will look like 3, 1, 2, and this as a null, And then second tree will look like 3, 2 and 1 and 1. And this would be null. So how many trees as a root? How many trees we can, how many binary search tree we can create? 2. So how many total binary search tree we have created? 2, 2 and 1. Only 5. So if we have 3 number of nodes, we can create 5. Whoever was saying 6, now you got understood why we can only create 5. Understood, guys? I think while we were discussing about it, you guys have also thought about the logic as Likhit was thinking. We are doing something recursive here. First thing, if you guys have observed, we are first thing, whatever we are considering every number here as a root. We are considering every number as a root. It means we have to traverse. We have to traverse whole, like 1 to n, we have to traverse. Correct? This is the first traversal which we need to do for each of element. Correct, guys? For each of element, we need to traverse. Did you guys understood the first line which I told? Everyone, why we need to do the first traversing? Everyone understood? Okay, now the second thing which you have observed, once we are doing the traversal, we are trying to create the left side or right side. Correct? You can see for one, what I did, once I consider 1 as a root, what I did, I tried to go for left side. I try to construct left side tree. I try to construct right side tree. Correct? That's what I did. Whenever I'm considering something as my root, I'm trying to construct a left side of it and right side of it. Am I right, guys? That's what I'm doing. Okay. So now once I constructed a left side of 1, we do not have any elements. It's a null. So we are simply returning out from here. When we have null, it's okay. Just return out of it. Now go for the right side. Construct the binary search tree. Correct. So for the right side, we got 2, 3. For the right side, we got 2, 3. So again, once we got 2 elements, again we need to construct the tree. Again, we need to construct the tree. So for 2, 3, again, consider 2 as a root, consider 3 as a root. So you can see, let's draw it again. No problem. Let's draw it again. So I'm just trying to tell you guys the logic. 1 to n, where n is 3. So our numbers would be 1, 2, 3. What I did, I'm starting a loop here. And first, at the first loop, I have taken 1 as my root. So 1 as my root. Now what I need to do, I need to construct a left tree and a right tree. Correct? So on the left side, you can see I do not have anything. It's a 0. We do not have anything. So what we did, we just simply putting a null here. But on right side, you can see we have 2 elements here. 2, 3. We passed both of elements 2, 3. Correct? So once we passed out these 2 elements, so you can see. Okay, let's I will tell you how we are passing both elements. But yeah, just pass 2, 3. Now we again got a small tree here. Correct? So we need to again follow the same logic. Now these 2 would be, first we'll consider 2 as a root, then we'll consider 3 as a root. So now here, first we'll consider 2 as a root, then we'll consider 3 as a root. Correct? So for 2, again we need to do the same thing. Construct the left tree, construct the right tree, construct the left tree, construct the right tree. Correct, guys? So once 2 is a root, on the left side we do not have anything, so we'll simply do the null here. On the right side, we have 3, so this would be one combination. Correct? While we are considering 3 as a root, so left side we have a 2 and the right side we do not have anything. Correct? You can see The same thing which we started for the 1, we did the same for 2 comma 3 as well. Now if we still we have something, we do not have, we have only single elements here. We only have single elements here. So for single elements we do not need to do anything. So that's why you can see we are also trying to consider the base case. Yes, we are also trying to consider the base case. But did you guys understood? Once I consider 1 as my root, you can see this is the tree, this is the final recursion looks like. And you know guys, once we will come back out of this, out of these recursion, this is one recursion. You can see this is one recursion, left subtree, and this is another recursion, right subtree. Correct? And these two recursions are running only for this part, this recursion. This is the right subtree, right? Let me draw it correctly. This right subtree looks like this because, correct guys, now you can visualize it. Inside this recursion, this is the first recursion, right? This is the second recursion, because see, this is one recursion and this is another recursion which is running here as well. This is the first recursion, right? Left subtree, which simply returns null sus. So no need to run further. But here for right subtree, you can see two more recursions are running. Did you guys got it? The circle part. That's how I want to show you how the recursions are running there. Okay. And now you can see, now guys, once we completed these internal recursions, once we completed these these internal recursions, we will be at this place. We will be at this place. Correct? We will be at this place. Correct? So now guys, let's just take one more thing, which is just take one more array just to keep track of just one array, just to keep track of how many possibilities as a when we are considering 1 as a root, how many combination it could create. Like simply not one. Whenever we are taking any element as a root, how many combination it could create, just to keep track of that information. Okay, that's why we are taking one list array. And in this list array, so see guys, first recursion, this recursion will run. First this recursion will run. So from here we will get simply null. We'll simply get the null. We'll get a node here. See guys, while we're returning null also, we'll consider that as a node. So here we will be returning null as a node. Okay, null as a node. Into the right side, let's look into the right side. Into the right side, we would be getting two trees. We would be getting, so you can consider this is a left list. Now go for the right list. For the right list, we would be getting two things, two nodes here, 2 and 3. Two nodes. One combination of 2 like this, one combination of 3 like this. Two combination of guys, are you getting it? Left list and right list, just to keep track the answers. Just to keep track the answers. I'm not telling anything, just to keep track the answers. So you can see on the right side, we have two answers here. One answer is when we are considering 2 as my root, then this answer is coming 2 arrow on the right side to 3. When we are considering 3 as a root, then we have this answer. Correct guys? So that's what for the 1 we have 2 3. So now we will what we'll do, we'll construct the one tree. See, we are trying to construct a tree for 1, right? Including left and right. So once we'll construct the tree for 1, it will look like this. First tree will look like this: 1 2 3, right? Yeah, 1 2 3, and then second will look like this: 1 3 and 2. Correct guys? So just at the end, once we got left and right subtree, we'll just try to add left and right subtree to 1 also. Then only we'll get the final answer for 1, how many tree we have constructed. Same will go for 2 as well. Same we will go for 3. We'll do the same logic again and again. And that's what guys the code is also. That's what the code is also. Now let me show you the code as well. So there are two base cases guys. There is two base cases. And before that, let me tell you how we are starting. So how we are starting. There are three pointers which we are taking. Start, end, and I. I would be our I would be our iterations. I would be our iterations. Like for 1 comma 2 comma 3, I would be at one position, second position, and third position. So I will always start from I will always point out to start position. I will always point out to start positions. And you know, when we will call the when we will starting calling this function, at that time we'll take start as a 1 and end as a 3. You know, once we'll so let me tell you how the iteration also happening. Okay, so let's start. So let's take start as a 1 and end as a 3. Okay, so let's run our loop. Let's run our for loop, which is start from I is equal to start and I less than end and I plus plus. Correct? So now it will run 3 times. It will run 3 times for this, for this, for this. Correct? So now once we are calling our left side, we will be always passing, always for left side, it would be start comma I minus 1. Start comma I minus 1. 1 minute, 1 minute. Yeah, on the left side, 1 minute, guys. Let me think about the left side. So left side for 1, see guys, for 1, the left side would be start comma I minus 1. Yes, yes, correct. Start, it's not for 1. Let's consider for 2. For 2, if 2 is here and start would be at this place. So yeah, and I let's consider this thing for 1 comma 2 comma 3. 1 comma 2 comma 3. We'll be getting this logic with 2. So let's consider 2 is here. So I would be at second position. Correct? I would be at second position. And our start will, yeah. So for left side, we want, yeah, start will still be 1. Start would be still be 1 here. And yeah, so start comma I minus 1. Correct. So wherever, so see, start is always going to tell you guys from where we have started. Start is always going to tell you from where we need to start, and end is always going to tell where we have to end. And I would be the element which is going to traverse between these numbers. So yes, so for left, it would be start comma I minus 1. So start would be 1 and I minus 1 will also be 1. So this only one element will be going for constructing the left side tree. And for the right side tree, I think it would be I plus 1 comma end. I plus 1 comma end. So end will always be 3 and I plus 1 will be 3 at this place. So 3 comma 3, which will be this element. Understood, guys? Left subtree and right subtree. Did you understood? Okay, so see, just consider 1 comma 2 comma 3. So for 2, what would be the left subtree? This part, right? And for the for what would be the right subtree? What would be this? So we have start and end. We have to use these variables to identify our left and right side, correct? And with that, we also running one loop of for, which is telling us at which position we are right now, at which position we are right now. So for I, it would be second position, right? Because we are starting our I from 1, not from 0. So I would be at second position. So now how will I get at the left side? It would be start comma I minus 1. All the elements which are starting, see, just take this element 1 2 3 4 5, right? Just take this example, guys. 1 2 3 4 5. So start will be at this place, end would be at this place, and you want to calculate the value for 3. So I would be 3 at this place. So what would be the left side here? So left side would be start comma I minus 1. Start at this 1 and I minus 1 would be 2. So this position, you can see 1 comma 2. For the right side, I plus 1 comma end. I plus 1 is 4 and end is at 5. So 4 comma 5. You can see all those ranges are going there. Now you guys understood how we are calculating, considering the left and right constructs of tree. Okay, now let's jump into the code directly. If you guys have understood all these things, I think I plus 1 didn't understand. So I plus 1 is this thing, right? On the right side, right now your I has 3rd position. You want to look for all the elements which are on the right side, which is you can see. So what you will do? I plus 1 command. I plus 1 command. Understood, Arad? See, right now you are at that 2nd position. You want to consider all the right side element. So what you will do? The next element from you to the end, all will be the right side. Understood? That's what. In case of more numbers. Yes, in case of more numbers, that would be make more sense, right? If you have more numbers here, 4, 5, 6, 7, all the at the right side, all 6, 7 will come. 4, 5 comes in because your end will be pointing out to 7. All more numbers will come 4, 5, 6, 7. Yeah. See, start and end are fixed. Start and end are fixed. Understood, guys? So now let's see the code, guys. Whatever we have talked about, same thing is happening in code as well. Let me show you. You can see I am passing n is equal to 3 to my function construct tree. Correct? So we are passing 1 comma n. So right now start would be 1 and end would be 3, right? Let me draw it here. So start would be 1 and end would be 3. Correct? Correct. So that's what we are passing to construct tree. Let's look into the construct tree. Do not look into these base condition right now. Just ignore these base condition. Okay. So now we are going to construct our tree. We have one list stack. Correct. So now what we are going to do? We are first going to run our loop, which is going to start from which is going to start from the start position and going to end into the end. So now this will run 3 times. I is equal to this will run 3 times. First for I is equal to 1, this will run I is equal to 2, and then I is equal to 3. Am I right, guys? Are we understood till now? Are we good? Yeah. So let's move. So what is the first thing we need to do? We need to go for, we have to consider 1 as our root. 1 as our root, and let's calculate the left subtree for 1 and right subtree, because we are going to first run the loop for this one, I is equal to 1. So it means we are going to consider 1 as a root. So once we are considering 1 as a root, we need to construct left subtree and right subtree. So that's what you can see in the next line. That's what I'm doing. Constructing the left subtree, then constructing the right subtree. And how will I pass the values? Because we are going to call the construct tree method only. And in the construct tree method, we always have start and end value. So now for the left subtree, I already told you about the conditions. Start comma I minus 1. For left subtree, always start comma I minus 1. So that's what it will be, start comma I minus 1. For the right subtree, you can see I plus 1 comma end. All the elements into the right side, all the element into the left side. You can see start comma I minus 1. All the element into the left side, all the element into the right side. Understood, guys? Are we good? Yes. So that's what the method is working, left and right subtree. Okay, guys. So now let's look into the base condition also. So the first base condition is whenever your start is greater than end. Whenever your start is greater than end, at that place push the null. Push the null. And wherever your start is equal to end, push that start node. Push that start node. So let me show you that also. Let's consider the one scenario only, one as the root. So one as the root, so we will be passing start comma I minus 1, start comma I minus 1. For the right side we will be passing I plus 1 comma start. Correct, guys? And right now, you know, start is 1, end is 3, and I is equal to 1. Guys, understood these three lines? All these things which are right now displayed, have you understood? Start, end, I value, and we are going to construct now the left tree. So now you can see, for start, it would be 1, and I minus 1 would be 0, because I value is 1. So 1 comma 0. So what I'm saying, whenever my start value is greater than end, just simply return the null. In my list, simply return the null. And that's what happening. You can see the first condition. Because you can see in left side, you are calling the recursion. Again, this construct tree will be called. Again, list will be empty at this place. Now, you are just simply checking this condition. If your start is greater than end, just simply push the null and return from here. Return from here. Then go for the right side. So now you have completed this time. Now you're going for the right side. So right now, right side, I plus 1 comma start. Your I is 1. And start is, sorry, I plus 1 comma end, not start. So your I is plus 1 is 2 and end is also 3. So 2 comma 3. 2 comma 3. So now both base conditions are not matching. Start is greater than end? No. You can see start is 2 and end is 3. So it start is not greater than end. My second base condition is start is equal to end. No. Start is also not equal to end. So again, we need to run a second loop. You can see, we are going to again run the loop. We are going to again run the loop. And I already told you, right? With the visually also, again, we are going to consider 2 as a root and 3 as a root. And we are going to do again same thing. So now let's first consider 2 as a root. So 2 as a root. So here I will be 2, start will be 2, end would be 3. Correct? You know that, right? These are the start and end we are passing. So I is equal to 2, start is equal to 2, end is equal to 2. And again, when we will, this would be when we will consider I as a 3, like second iteration. So here start will still be 2, end will still be 3. Correct? Now run the loop for them again. Again, go for the left side. So in left side, what we are passing? Start comma I minus 1. Start comma I minus 1. What we are passing on the right side? We are passing I plus 1 comma right. Same logic. Whatever we did in the here, I plus 1 comma end, sorry. I plus 1 comma end. Same logic. I plus 1 comma end. Now let's consider what is the start here? Start is 2. I minus 1, which is 2. I minus 1, which is 1, sorry. Because I is 2 here. Again, see guys, same condition. The first base condition. First base condition. Start is greater than end. We will be simply returning here null. This one is done. Now let's go for this. I plus 1. I is 2, which will become 3. End is 3. Now second base condition is coming here. Now second base condition. What was the second base condition? When your start is equal to end, just push your start node and return it. So what is your start node, which is 3? So return the 3 from here. Return 3 from here. And this both return will be completed. We will be going for the second iteration, second for loop iteration, which is this one, right? Already we have traversed 1. Now we are going with 3. So now let's go same for 3 as well. Left side and right side. This is left, this is right. What is the code for left side? Start comma I minus 1. What for the right side? I plus 1 comma end. So what is start? Start is 2. What is I minus 1? Which is 2. See guys, when start and end are equal, just return the start value, which is 2. I plus 1 comma end. What is I here? It will be 4. 3 plus 1 comma 4. And end is 3. You can see start is again greater, return the null. Now guys, you have 2 lists from here. Correct guys? You have 2 lists. You have already have for this, you are running for this 2 for loop. This one and this one. Now they have given these answers to you. Till now, are we good? In code where we are fixing root. So Hariharan, the fixing of root is happening when we are running our for loop. Our for loop is the fixing the root, which is fixing the root. Whatever the value of I is, that is our root. Understood, Hariharan? Whatever the value of I is, that is our root. What was the second condition? Please. Second condition was when your start is matching with end. Whenever your start is equal to end, that is the second condition. Just push your start element there. Just push your start element there. Understood, Vishal? Just push your start element there. Okay. So now guys, wait. From the left side, we got one array, which is null. From the right side, we got one array, which is here. Correct? And this is the I is equal to 1. When I is equal to 2, sorry. I'm talking about these two recursions. I'm right now at this recursion. Not at this. This is separate recursion. This is separate recursion. Correct? Where we are considering I as a 3. 3 as a root. Here we are considering I as a 2. So now you can see for I is equal to 2, we got two arrays. On the left side, we got null. On the right side, we got 3. And here our root or I is 2. Correct, guys? Correct? Everyone understood? So now let's construct a tree. Let's construct a tree. We have not constructed a tree. We just find it out. For 2, left is null. For 2, right is 3. But we have not constructed it. So for construction, we will be simply running two more inner loop. First loop on left, then on the right. So simply on the left, because it's empty, it will be running only one time, and on the right, it will be running second time. So what just simply we need to do node dot left is equal to left, and node dot right is equal to right. Let me show you where it is happening. It is happening after constructing a tree. You can see once we got left side subtree, once we got right subtree. Once we got this left array, once we got this right array, then we are trying to construct a tree. And you can see I'm just running one loop on all the elements in the left sub array and all an inner loop on the right sub array. And then we are trying to simply constructing it. You can see we are considering I as a root. You can see making value I as a root. So that is our root. Then we are simply adding whatever coming into the left side, left, right, simply constructing a tree here. And then after that, how many trees we are constructing, we will be pushing it into the final output. That would be output for I as a root. That would be output for I as a 2, how many tree it can create. I as a 2, how many tree it can create. That would be his final answer with this list. The same will happen for 3 as well. Same will happen for 3 as well. For 3, there are 2 arrays are coming. One on the left side and on the right side. We will simply construct a tree. So how will we construct a tree? We will run loop from the left side. So this is the left array and this is the right array, which is null. Guys, this null is in one element. You just not consider this is not a node. I am again telling you, whenever we are pushing a null, this is a node. Let me do it correctly. New node. Sorry, I was not doing it also. This is a node. So do not consider it's nothing. Yeah, that's why we are storing. That's why we are storing. No. That's why I'm telling you that that's a node. So do not consider that loop will not run. This for loop will not run. Do not consider this for loop will not run because left array has null. No, left array has a node. This is a node which does not have any value. This is a node which does not have any value. This is a node 2. So now what we are doing? We are running a loop into that. So one time loop will run. I'm considering for 3 as a root. So I is equal to 3 here. So first we'll construct we'll run 2 loop here. One on the left sub array and inner loop on the right sub array. So loop will run like this. I is equal to 0. I less than left array dot length or I plus plus. correct? And same go, internal loop will run for right subarray j plus plus. And then we'll first construct a tree from our root node. So 3 will be there. Then we are adding left element into it. So left would be 2. So 3 is a 2. Then we are adding right element into it, which would be null. And then both loop will be completed, because this loop will also run one time because it has only one element, and this left will also be running one time. So both will run one time, and will at the final answer as a list, we will be pushing this tree 3, 2 and null. And that's what we are pushing it here. That's what we are pushing it here. You can see list dot push. We are pushing as final node where 3 is our root. Got it, guys? Why can't left inside right loop? See, we will start from the left side. When we try to create a loop, when we try to create a tree, we start from the left. See, you know, always the smaller element come into the left side, right? Okay, by the way, question is nice. Why not start loop from the right side? So let's think about it. What will happen if we start loop from the right side? 1 minute. Let's think about it. Or I think we can do from both sides, but let's just think about it. So if we have in left, let's consider 2, right? And if in the right, if we have 3, 4, 5, correct? So now what will happen? So, and our root node, we can consider it is 6, right? So now for 6, so right loop will run, right? Right loop will run, correct? So this is our right, I am considering. This is our, 1 minute, guys. This is our left, this is our right. So let's first correct the values. So let's consider, yeah, let's consider 2, and let's consider 3, 4, 5 as a right. Let's consider 1. Yeah. So left is 1, and in right we have 3, 4, 5. Correct. And we are saying why not start from right? So we can start from right also. So this is our loop. So this is first loop, right? 3, so the first loop for I will run 3 times. 3 times, and for the j it would be 1 time. So let's run it. So our root is 2 here. So 2's left would be 1, correct? And 2's right would be 3, correct? Now let's go for 4. Let's go for 4, right? So 2 would be first one, and yeah, left would be 1, and it would be 4, correct? Now let's see other thing. 2, I think yes, we can run. See, it would be 5, correct? These are the 3 trees which we can construct. One minute, guys. Let me think about it. Are we missing anything? Yes. So 2 would be right. Would be our first loop. So we start from 3, and we'll be having the 2 there. Correct. Yes. So 3 would be there. Okay. And the second loop will run for the left side. Correct. And we'll create the 2. Yes. We can go from both sides. Hariharan. We can start our loop from the right as well. It will, I believe it should work in the same way. But yes, I have to check a little bit more, but I'm thinking right now that it should work in both ways. Okay, Hariharan? Yeah. We can go, we can construct from the, like, right can also be first. It's not like that left has to be first. Okay, so that's what, guys. At the end, we will be getting our final answer in the list. Okay, so I have already put the console. So let me show you guys how it is looking like. Console.log start comma end is here. Here we are printing a root as well. At the end, we are printing a list as well. So let me show you how that looked like. Okay. Node problems tree unique bsc.js. Let me now show you from the starting. I know this answer is a little big, yeah. Now, let's see. So first time, you can see start and end, 1 comma 3 is coming. Okay, 1 comma 3 is coming. Now they have crossed these two conditions. Now we are going to construct our left and right subtree. So for the first time, left side, what will be our start? Start would be 1 and I minus 1 would be 0 because I is 1 right now. So that's why 1 comma 0 will go. And 1 comma 0, you know that start is greater, we will be returning null. So that's why you can see 1 comma 0 is not returning anything. Now next time 2 comma 3, where because now we are going now now we are going to the right side because left subtree has not written anything. So we are going into the right side. Still 1 as a root. Still 1 as a root, we are going to the right side. Correct? So now I plus 1, which become 2 and end is still 3. So 2 comma 3, two elements are there. These two conditions will pass. So now once 2 comma 3, so again you can see 2 comma 1. You see 2 comma 1, then 3 comma 3. Already explained, right? Similar thing. Here also you can see. See, first time 1 comma 0, then 2 comma 3, then 2 comma 1, then 3 comma 3. You can see everything here. The same way 1 comma 3, 1 comma 0, 2 comma 3, 2 comma 1, 3 comma 3. Now both of the tree has been completed. Both of these for 2 comma 3, where we are considering 2 as a root, left and right has been completed. So that's why you can see after completion I am putting my console.log again. So you can see I as a 2, which is root node 2. Left side coming, everything is a null. Left side everything is null, right? You know that, right? On the left side, yeah, you can see this is the left side, 2 comma 1, everything is a null. That's why you can see everything is a null. And the right side, you can see 3 as a key and left and right as null. So you can see right side 3 only you are inserting. And then we are going into the right side, which is 3, where we will consider I as a 3. So let me show you that also, guys. Now let's see 2 comma 2, 4 comma 3. See 2 comma 2, 4 comma 3. And then once we have left and right, let's combine it. Let's combine it. You can see this is the left tree, this is the right tree. You can see this is the left tree 2, this is the right tree. Now we have left and right. Let's combine it. Now we have left and right. Let's combine it. So let's see. After combine, I put console again. You can see here. This is the after combine. So you can see 3 as my root. At the left side, it has these many nodes. At the right side, it has these things. And similar, once we have completed left and right both, then we will be looking for 1 as a root. And that's what finally you will see for the 1 as well. Both things. And then we will go further for 2. Now all the condition for 1 has been completed. Now let's consider 1 as I is equal to 2. You know your first loop 1 comma 2 comma 3. This one, where is that? On the top. Where I written somewhere, right? I is equal to 1, I is equal to 2, I comma 3. Yeah, this one. So this one is completed. Now we'll go for I is equal to 2. Everything same will happen there as well. And at the end, you will be getting answer. Similar way it will be running, and at the end you will be getting your list, final BST tree, and then you will be returning the length of it. Because you need to tell, right, to the user that how many unique BST you can create. Understood, guys? This question was little tough, I know, but I tried my best to explain you guys in easy way. I hope you guys have understood. And this question has been asked in like bigger organizations as well. I tried to explain that also with little bit easy way, but I think this question you guys will only get when you guys will practice it. So you just need to now practice it. Practice it with your copy pen actually. When I was understanding this question, I just tried to solve it in my copy only. Then I only understood the coding part and logic part as well for this. Okay, guys. Yes, actually. Okay, guys. So now we can go for a break, and then we can come back and then start a new topic today, which is our hashing. Okay, guys. So right now it's a 9:23. So let's come back at 9:38. Yes. Yeah. Let's go for dinner. Let's come back at 9:38, and then we will start a new topic, which is hashing. New node I. It will create a new node. You see, Hariharan, this is the class node, correct? So when we have a class node, when we do new node, it will create a new node for us, which have three properties: key, left, and right. And that's what we are doing everywhere. You can see new node start, or new node null. It will give us a node which will have these three properties. When we are passing null, it means this data is null here. As a key, it has a null here. As a key, it has a start here. And then we have a I, which means we are creating a new node as a root value. Yes, I is index. And as I told you, we are going to consider index as a root value. So that is going to create our root node. Yeah, as it happens. I don't know what happens suddenly. Yes, it will take one first. Yes, it will take one as a root. Then second time your I will going for two. It will consider two as a root. Then it will be going for three. It will take a three as a root. Yeah. I don't know why I'm getting this, but something. Yeah, I don't know. Something like in old say they are saying some. Yes, am I remembering? Some, I don't know what is happening. This I'm drinking water as well. It happens sometimes. No problem, no problem. That's okay. Uh, so yes, Riaz, actually, yes, it happens, but on paper side, but yes, once we understood the logic, then I think it makes easy to write the code as well. That's how I feel as well. And when we spend little bit time, automatically actually coding become little bit easy. Only the logic creation become difficult. Once you understood the logic part, I think coding creation is writing code is not difficult. But yeah, logic thinking is little bit tough, which comes, I think, after spending some time or after practicing it. And still, I think nobody is perfect actually. Sometime everyone is stuck somewhere. Yes, that too, that recursion is tough. See, Likit, actually, I personally feel recursion not as a tough because I know that recursion is going to make the same call again and again, and we just need to change our input values. So whenever recursion questions comes, I cannot do it in my mind, guys. I always use my copy for recursion. All this while solving all the recursion problem, I most of the time try to use my copy. And I always try to think about how can we see in the recursion, we have to base condition, two or three things which you need to remember: base condition, and second time your inputs are changing. You can see in this question also, in this question, guys, as well, you can see your inputs are changing every time, start and end, every time they are changing. And third thing in the recursion happens, you need to minimize your input. You need to minimize your input. In this case, we are not minimizing our input, but definitely in this case, our input are definitely changing. So I think two important things are there: base condition and your input should change, even through minimizing or any other way. In this way, we are see even here also we are minimizing and increasing I plus one, I comma minus one. So every time, whatever recursion question you will see, every time these things are happening, base conditions and your input are changing every time. Okay, guys, so that's what. So let's go for break now. So right now it's 9. 28. So let's come back at directly at 9:40, and then we will. Sorry, 9:28 is right. So let's come back at 9:43. 35, 30, 40 minutes in single questions. Yeah, if it is happening, if it's okay to take a lot of time in single question, something will happen. It is happening sometime, then it is fine. Because I think in the interview also they give 30 minutes to hard questions. 30 minutes or 35 minutes to hard questions, yes. I think if it's happening 30, 40 minutes, it's good actually. Sometimes when somebody is starting, it goes for 2 hours as well. It's like if right now it's happening 30, 40 minutes, it means it's fine. Sometimes it like who is very dedicated. See, right now we as a like very like eager person, when we are not able to solve any question in 30 or 40 minutes, 30 or 40 minutes, so we just simply go for answers, right? 30 minutes is enough. Like I think, yeah, yes, I think see it happens actually. Sometimes we spend I think 45 minutes also or not able to understand the logic, how to solve it, or might be some edge cases are failing. It happens. But yeah, so we are creating this tree using pre-order traversal, right? Creating this tree using pre-order traversal. Left, right. So while we're constructing a tree, we are left root. 1 minute. Let me check. So root, left, right. So first we are adding all the right actually. You can see uh, uh, Hariharan. So first you can see all the right side has been added. So it would be, I think, not pre-adder. So see, first root is there, and then we are adding all the right, and then we are adding left. That's how this code is running. So you can consider root, right, left. You can see left has been added one time only, but right has been added every time. So root, left, right. But you can see we are running it inside the right loop. So every time right is being added there. We did in console, okay. Oh, this one, this pre-order part. I was trying to traverse the route. That is not related. I was trying to traverse the route. I was just trying to traverse the route. That's the different thing. Okay, guys, so let's go for break. I think we have already spent this much. So let's come back at 9:45. Okay, let's come back. Hello, guys, can you see me? Great. Is everyone back now? Let me share my screen meanwhile. Okay, so great, guys. So we have already completed now the binary tree topics. Okay, so now we are going to move into the next part of topic. And most of the rest of class, which we are going to do, is going to be mostly theoretical and conceptual. We are now going to understand what is hashing, is hashing as a data structure, what is hash table, why we use it, what are the applications, and all the theoretical part we are going to discuss it. Okay, so so let's start, guys. We have already, I think we have told right to come back at 9:45. So now it's 9:45. Okay, so guys, let's start with understanding one problem or one scenario. Let's try to understand with one scenario, and because now this is going to be a little bit like theoretical or conceptual, so I want you guys also to respond so we can collaboratively answer some of the queries, and then we can understand the concepts here in little bit better way, rather than I continuously speaking it and you guys just hearing it, something you are able to understand, something you're not. So that would be bad way. It would better if we both communicate and collaborate. Okay. So let's try to let's try to start with one scenario. uh, we got a lot of books. Okay, we have got a lot of books for our library, right? And now we need to now we need to find a way to store these books in our library, so we can, and you can understand, we have not we do not know how to do in the library till now. We are just starting it. Okay, it's just the initial phase when we got a lot of books and we want to keep it in our library so everyone can access it. Okay, so what we need to do here, so when we got a lot of books, so we need to find a way so we can store them in a way so people can easily access them, right? That's why we brought all the books in our library, so people can easily access them. So you guys tell me, what would be the best way to store our all of these books according to the data structure which we have already read it, which we have already read or completed, which we have already completed. What would be the best way to keep all these books at one place? So somebody is saying storing them category wise. Okay. Placing them racks alphabetically. Okay. Stack or genre wise, like their books genre is also there. So that wise. Okay, guys. That's totally right. But if we talk about our data structure, so we started with arrays, correct? Then we started with linked list, correct? Then we started with stack and queue, correct? And stack and queue, it's just the same like stack, arrays and linked list, but just a different way to keep the books, keep the informations in those data structures, right? So stack and queue are not different than the arrays and linked list, right? Stack and queue are not different. They are just telling you different way to keep the informations. They're same. Then we have read about the binary trees or trees, right? So in the if in the top of it, we have three things here: arrays, linked list, and we have uh, what was the another one? The trees, right? So let's talk about the trees. Do we really need to keep our books in a trees pattern? What trees says? Like one book is here, like history book is here, then just go for, like the tree says, right, that all the different books can be easily connected. But do we need to keep in that way? Like one book of tree could one book can be in one rack, and then second book of the same type will be connected. I think tree does not make any sense here. Correct. Let's come back to linked list. Correct. Linked list is also in the similar way, but the same. See, linked list and arrays are also going to give you the problems. In arrays, I know you can simply store all the books like in index wise, like all the history books based on your categories or based on your ISBN numbers or based on your alphabetically also. You can store them in the you can simply store them in the arrays, right? Same in the linked list also. But linked list, what linked list says, that linked list and trees, I think they at the end, at the memory label, they are at the same place, right? In the linked list, you can only go into one direction, but in the tree, you can go into multiple directions. So linked list and trees, they are at the end, at the memory level, they are like looking like same. Correct. But now if we talk about the arrays, so in arrays, there is one problem, guys, that the finding part. If you want to find any of the books according to the arrays, what you need to do, you need to start like from the zeroth index. Then every time you need to find it out, that particular book, is that particular book is matching, is that particular book is matching, is matching, is matching. If it is matching, then you will pick that book from that index. Correct, guys? That will happen in array. And if that array is sorted, like based on alphabetically or based on category wise, you know the categories, but still that will take binary search. Like at that time, we can take the binary search. We can take the binary search, and that will bring our books into n log, login. Sorry, it will bring the time complexity to login. Correct. That was the data structure we have read till now. Stack and queue, these are the same data structures, right? Arrays and linked list. It's just a different way to keep things. So that's why, guys, there is one more better way. There is one more better way to store all these books, and that comes with hashing or hash table. So what happened here? What happened here? All the books which you are going to keep it, we will first hash them. We will first hash them. Hash them means somehow, like somehow we will just simply add a cheat. Add a cheat. You can just I'm trying to explain you. In each of books, you can just add one cheat there, right? And that cheat will help you directly to access that book. That cheat will directly, yes, it that cheat will provide a unique identity to that book. Unique identity to that book. You just need to verbally say, it just there is one machine is standing in front of you. You just simply need to say, give me Lord of Rings, give me Lord of Ring book. So what that machine will do, it will take your input Lord of Ring, it will convert into the hash, it will convert into the unique identity, and it will directly access that unique identity from array. Like, just consider, in array, what was the problem in array? In array, your problem was the searching. You need to start from the starting index, correct? But if somehow you understood this thing, that at what index what you are saving, you can directly access the index in array, right? Guys, let's come back into the array one again. In the array, what was the problem? Problem was, you are not easily you whenever you want to search anything, you have to start from the zeroth index. Am I right, guys? You have to start from the zeroth index and then find it out. But if I'm telling you, if I'm telling you, at this index this book is residing, or this book is there at this index, do you need to traverse it still? Do you still need to traverse it? If I'm telling you, at this index this book is, correct, no need to traverse it. You can simply go to that index and pick the pick the book from there. That's what, guys, that's what the hash table is. That's what the hash table is. Hash table uses two things. One is your array, and second one is hash function. Second one is hash function. So hash table is a data structure, guys. Hash table is another data structure which uses two things. One is an array for storing your information, and second one is a hash function. And that hash functions helps you in two things. That hash function helps you in two things. First, it tells you the position. Where are you going to store these things? Okay, hash function is going to tell you that at which position you are going to store this information. Understood, guys? What is the hash table here? It's similar like array, but just one additional thing into that. And that additional thing is hash function. Like content in the book. Yes, that's very nice example. If you're reading any of the books, in the first or second page, you know, right? The heading and the numbers, right? You see that, and at page number 36, this chapter is starting. That 36 is the index there, or the hashing value at the 36 page number. You know that what value resides. Understood, guys? So that's what and why we are doing this. We are doing it for easy and constant time access. We can access that element in constant time. Earlier in array, the if that array is sorted, we can use log n time. Or if that array is not sorted, we, in worst case, it can go for n. But now, with the help of hash function and arrays, now we can access element in constant time. That's the benefit. That's why we did all of these things. Okay, that's what the hash table data structure is. Understood, guys? Everyone understood? What is hash table here? Okay, now let's understand, guys. Now let's understand what is hashing. What's the meaning of hashing? It eliminates the need for searching. Yes, it eliminates it. But it uses the hash function as well. So that's what we'll talk about it. But you can understand, for hash table we need two things. For if we want to implement hash table, we just need two things. One an array and simple one function. Correct? Yeah, Joseph, that's what I'm telling, right? In hash table, we need two things. One is your array, and second one is the hash function. And that hash function is telling whatever input is coming, at which place you need to store it in array. At which place you need to store it in array. And let's give you one more example also. Let's give you one example also. As I told you, you guys are able to see my screen, right? Yeah, let's just take one technical example also very quickly. So if I'm taking my array as empty, because this is the array where we are going to store the informations, correct? And now just consider I have these numbers, these values: 11, 12, 13, 18, 19. This is my books ISBN number. You can consider these are books ISBN number. I want to store these information so I can directly access them. Correct. So what I will do, for I will create my hash table. And as I told you, hash table needs two things: one array, and second one is a hash function. And what this hash function does, it will tell us at which position in array is stored this information. And how it does that. There are a lot of hash functions. The famous hash function which I am telling you, which is use the key, use that particular data which we want to store, and take the size of table. So right now I'm just considering size of table is 10. Size of table is 10. So just take the key and mod size of table. Size of table. So now you can see it is key is 11, mod 10, it's a 1. So in hash table at index 1, 11 will be stored. And you know that in array also, in array there will be multiple indexes, right? So at one index, 11 will be stored. Same for 12. For 12, our hash function is giving position as 2. So at position 2, we will be stored 12. Same for 19. 19 mod 10 will give us 9. So at 9 position, we will be getting 19. Understood, guys? Understood this thing first, what hash function is doing, and what is why we for creating a hash table, why we need two things. We need one array and second the hash function, and you know the purpose of hash function also. Now guys, who was asking, Hariharan was saying, is hash function asynchronous? We can create it. It's depend on us. We can create function asynchronous as well, synchronous as well. But the hash function should be synchronous, because what is the meaning of if you are asking the question about asynchronous and synchronous, I hope you know the difference between them. So with that understanding, because you know the difference of asynchronous and synchronous, and because we already covered it into the previous modules. So the synchronous means what hash function is doing. Hash function is giving you index. If you did not receive the index, where you will store it? Asynchronous means it will give you later once it got it. Asynchronous means it will get it later. But what you will do then? You cannot store it, right? Hash function is giving you index, giving you positions where to store the value. So that's why hash function should be synchronous. If they should give us the value, then we can go for the next step. Understood? Yes. See, we can create it. These are functions. These are functions. We can create it. But does it make sense? Does it fulfill your use case? Does it fulfill your use case? Not, no. Because why we are using hash function? We are using hash function to get the position index where we have position. So why we will wait? Asynchronous means wait for some minute, and wait for some minute and do other things. You know the example I told you, right? Of an asynchronous, getting Maggie and tea at the same time. We don't want to do that, right? Correct? Yeah, that coffee and Maggie. Yeah, that was. So we don't want thinking. We want to first complete the first thing. So that's why it should be synchronous. Okay, now the second question Likhit was asking, there was, can a one index. So guys, let's take the same example. I will talk about little bit deeper into that. I'll just go through on top of that. So you can see if somebody is providing us 22, right? So 22 mod 10 will give us 2. At this position, we already have one element. Correct, guys? At position 2, we already have 12. And we now got 22 as well. So this is known as collision. This topic, this scenario is called as a collision. And there are lot of collision resolution techniques are available. There are a lot of, see, every time collision will happen. Every time, not every time, in every hash function there would definitely be there would be definitely somewhere collision will happen. And so collision is not bad, because collision will definitely happen. So collision is not bad. We need to find a way. We need to find a way to reduce our collision. We should find a way so we can reduce our collision, and that's what we will discuss. That's what we will discuss. Okay. So guys, first we understood the hash table. I think I have explained you 2 3 things. First, I explained you the hash table. Then I explained you why how can we implement a hash table with the help of arrays and the hash function, with the help of hash function. I also told you the use case of that, why we need it. Correct. Let me tell you one more use case, guys. Let me tell you one more use case why we need hashing. Okay, but before that, let's give the definition of hashing as well. Let's understand the definition of hashing, general definition of hashing. So hashing is a process. Hashing is a process which take a string and convert it into a alphanumeric fixed size string. Alphanumeric fixed size string. It's a general definition. I'm not talking about the hash table. I'm just simply talking about the general. I'm just talking about the general definition of hashing, which says that it will just take any length string. Any length string. Yes, it will just take any length string, and once you will pass this any length string to a hash function, it will give you a fixed size alphanumeric string. That's the definition, general definition of hash. That's the general definition of hashing, guys. Okay, so let's see, if I'm giving you like any book name, like Lord Ring, or the better example is, we use the longer words in a short way, like talk to you later. What do we say? TTYL. We can say this is also hashing, right? In one way, we are just converting a whole big string in a smaller 4 letters. So talk to you later, TTYL. How are you? HRU. You can see how we are passing how are you as a string, and then we have a hash. You can consider we have hash function in the middle, which is converting it into the like first letter. Like hash function we can implement in our own way. Here what we are doing, in whole like sentence, we are taking first letter and then we are giving as a result. I don't know what is happening today. Continuously hiccups are coming to me. So, so this is the general definition of hashing, guys. Okay. So now we have understood, right? And hashing has been used at lot of places, not at one or two places, lot of places. And the best, and the best example to understand hashing is through the login credentials or your password. Not sure who is that. Who is that? I'm not sure. Okay, so let's take guys another example, which is very famous example. My friend has borrowed from me. I'm not, by the way, thinking about them. Okay. So let's understand the nice example. I think you guys have already seen it, or as a web developer, everyone should know that example. Whenever you create any login credential, at that time you ask for two things, right? And that two things are username and password, correct? So in your database, if you will keep, like, if somebody, like, if there are two users, like, just take you guys names only, Vishal and Parag. Just take one more name, Likhit. Likhit is there. So you are three users, right? And you guys have some password. Like, your password is ABC123. And same password, Likhit also have ABC123. And Parag has like XYZ123. So first thing, guys, we should not keep our password, whatever user is entering, in similar way in our database. Why not? Because if somebody has a database access, he can simply read your password and he can simply do the login. Correct. So that's why first thing, it's a general like knowledge for you guys also. When you're developing any application, never never save your password. Like, as an application developer, whenever something is coming from the UI, when some password is coming from the UI, you should never save it directly into database as a text. You should always hashed it. You should always hashed it. Yes, we use the bcrypt.js for hashing it. So guys, after hashing, what I told you, the definition of hashing, it takes a string and pass it to the one hash function, and then we got one alphanumeric. So let's just randomly x, y, z, 1, 2, 3, a, b, a, c, something random string we will get it. Correct? Same string we'll get it here as well. And this will be different. Guys, now two things you should remember for hashing function. Two things you should remember for hashing function. Very important properties of hashing function. First thing is, once you got your hash, once your hash function, guys, remember this thing. This is important actually. Once your hash function has encrypted something or has provided you hashed, has like this particular thing is known as multiple names actually. This is called message digest. This is also known as hash value. This is also known as checksum. Multiple names has given to this. So once you got your hash value, there should not be any way to get the original string back. Once you got your hash value, there should not be any way to get your original string back. That's the first way. That's the first property or first characteristics of a hash function. Every time remember, once you got your hash value or hash, you have to create your hash function in that way. You have to create your hash function or encryption in that way that once you got the string, you should not get back your original string. Okay, that's the first property. And second property is also important. Second property is, if I am passing same string again and again to that hash function, I should get same hash value again and again. Like infinite time, if I pass same string, if I'm passing ABC123 to the same hash function, if I'm passing, see guys, same string, same hash function should always return the same output. Same string, same hash function. it should always return the same output. That should be your hash function characteristics. These two characteristics are very important. Okay, first characteristics, if you got your hash value checksum or message digest, there should not be a way to get back the original string. There should not be a way. Otherwise, you can some see, if there would be any way, if in your database you are storing this thing, if there is any way I can convert back into this string, then why we are storing in this way? Why we are storing that has a string? Okay, we can store that generator has to not allow them back to its original form. No, we should store the generated has to not allow them back to its original form. I didn't understand what you're trying to say here, Vishal. But the meaning, what I am trying to explain here, that once you get your hashed value, you should not there should not be a way to get back your original string. That's what I'm trying to explain here. Okay. So everyone understood these two characteristics of hash function? Yes. So guys, for XYZ, we'll get something else like ABC, XYZ, 1, 2, 3, 7, 8, 9, some string like that. But for this hash function, where Likhit has also provided ABC 1, 2, 3, second property will work and we'll get the same string, same hash from the output. Correct? Correct? Correct. Likhit and Vishal's password is same. So now we'll get the same string, same has the string as output. Correct. But this is again a problem. This is again a problem. If Likhit has a database access, and he looked into it, he will check that, oh, my password has and Vishal password has is matching. It means, it means, it means we both have same password. Correct? We both have same password. Yes, it's a collision also. You guys are. But this is a problem, right? That because why we are storing our password in database in hash format, said nobody can understand, even not the database person. There should not be a way so database person can also understand. Correct? So guys, what we will do while creating our once we get ABC123 in our code, I'm just see, this is nothing related to hashing, just telling you something, telling you the applications of something, telling you some applications of these hashing and these things, nothing related to the hash table. We're just telling you the application of it. So what we'll do here, how we'll solve the problem, whenever any password is coming, we will append some random character into that. So like here, we will append XYZ into the ABC123. Here, we will append like I12. ABC123 will append something X12. Now we will be getting different hashed value. And this is known as salted hashed. Salted hash. And this is called salt. These random things are salt. Now nobody will be able to understand from the database what is your password, because every time unique value will be coming to you. That's how guys you will also be that's how you will also generate that's how you will also create your server code. That's why I told you this way. We can use username and password. No, username and password and check that everyone enter different user. Yes, that's also right. That's also right. That's totally right. Yes, yes, yes. We have used it in there as well. Salt. Yes, that's right. Understood, guys? This was nothing related to that. I was just telling you the application of the has or hashing. You know, guys, these let me show you this also. You guys are able to see my screen, right? Yeah, you see these SSL certificates. These are also hashed. If I go into the connection is secure, and if I see the certificate, you see these are SSH values are coming. These are hashed values are coming, which are keeping the information about the websites. These are also happening through the hashing only. These are, I'm telling you the applications of hashing. This is also one application of hashing. Your password encryption is also application of hashing. Your see, when you chat in WhatsApp, they say your chat is encrypted. That's also application of hashing. Lot of places wherever security comes into the picture, every time you are talking about the hashing. Did you guys now fully aware of hashing part? Are these your fingerprints? Where? You're talking about the certificate one, Vishal? Guys, with the fingerprints, I also got, now recently, digital fingerprints has started. Digital fingerprint has started. That's also we has it and then store it into the database. Once we keep our like thumb here, we take it as an input and then we pass it to our hash function and we then get back our hash value and then we store it with my username or user identity. So that's why you can see in the blockchain, in the blockchain also, for keeping our blocks immutable so nobody can change, we use the hashing only for in blockchain also. So that's why guys, lot of places hashing has been used. It's like whenever we talk about the cryptography, whenever we talk about the cryptography, encryption, decryption, everywhere we are using these hashing fundamentals. Everywhere we are doing using these hashing techniques. Now, are we good and confident with the hashing part, guys? We use phrase keys in crypto as a password. Yes, it could be considered as a salt, which I told you in the earlier example, to make our key little bit more strong. Yeah. Yes, acha, okay, you are telling, okay. Yes, in MetaMask, I have used it. You can see in the UI, right? This is the MetaMask on the here, on the browser extension. So yes, for login into the MetaMask, we use the phrase key. Yes, that phrase key also first converted into the hash and then verify through the MetaFace server, MetaMask server. That's also right. So that was actually all the application which I want to tell you about. So see guys, for creating any hash table, important thing is your hash function should be, see, for creating any of the hash table, what are the some of the important step here? The important step is your hash function should be like strong. Your hash function should be in a way so you can quickly access the elements. Or see, if you have one hash table, so let me draw that. Let me draw that. I want to explain something to you. So if we have a hash table, like I'm just taking a small size, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So hash table size is 10. So if you want to really use this hash table, so whenever you are storing the information, it should be equally distributed, right? So like first it should be three. What should first key should be at 3 position, then 2 position, and 7. Like all the positions, minimum collision should happen because your hash function is the one who is giving you the positions, and based on that only, you are going to see that how quickly you are going to access the element. See, collision will definitely happen because you need to, because always your hash table will be limited size and your string could be any length. Your string could be any length. Definitely collision will definitely happen. So collision is not a problem actually. That's why you will see that collision is not going to be happen. in the, you see, there are ways to recover the collision. We will talk about it. But I want to first tell you guys to think about collision is not a problem. Collision will definitely happen, but we should try something while we are creating our hash function. We should try something so we can reduce that collision. Okay. So now, guys, let's talk about first collision, then we'll talk about the hash functions. Okay. So guys, while collision will happen, there are two techniques which we used, which are very famous. While we are having the collision, there are two techniques which we use. One is called open addressing, and second one is called separate chaining. Okay, let me tell you. So two techniques are there. Two type of techniques are there. One is called open addressing. Second one is called separate chaining. So first, let me tell you the separate chaining one, which we, because that one is easy. That one is easy. Okay. So let's go back to the previous example only. So guys, there are two ways to handle. Now, guys, I am going to talk about now how to handle the collision scenarios. Okay, everyone, till now, see, before moving into that, are we good till now? Whatever we discussed, are we good? Then let's talk, because that's the next topic we are going to move into, the handle techniques of collision. Good, right? Okay. So now let's understand the techniques of solving the collision. Collision will definitely happen. So let's talk about the ways how can we handle the collision. How can we handle it? How can we handle it? We're not talking about the hash function right now. Collision already happened. Now we are talking about the ways to handle it. Okay. So the first way is called chaining. Simple chaining. So what happened, guys? So now 22 mod 10, 2 comes, right? So already 12 is there, correct? So what we'll do, we will add 22 after it. That's what the chaining is. Now if 32 is coming, again 2 is coming, we will add 32 here. Then like 49 is coming, 9 will get, we will be adding 49 for that. So guys, to implement this functionality, we use the linked list. We use the linked list. Yes, this is the chaining way. This is the chaining strategy to handle the collision. At any index, you can see, so when collision happens, so there is definition for collision also. Different input, same hash function, gives same output. That is collision. That is known as collision. You can see 49 or 19, different input, but same hash function. The same hash function is giving the same output. That is known as a collision. So whenever collision is happening, so for handling the collision, we are going to use right now here the separate chaining. We are going to use separate chaining here. And for implementing this separate chaining, we are going to use linked list in our background. Okay, guys? Understood? Then 9, will they be sorted? So for, see, no, they will not be sorted. We see, because it's a linked list, right? We are going to store it, and we can think about something. We can, like whenever new element is coming, we can add it from the back side. Or if new element is coming, we can add it from the front side. That depends on us. But you know, the the concern is here. Now it's not O1. Now it's not O1. Correct? See, earlier when we were trying to access any element, it was giving in the constant time. So see, if I talk about the 11, if somebody wants to find out 11, it exists in the data structure or not, we will do, we'll pass this 11 to 11 to our hash function, we'll get 1, and we will go into the hash table, fetch the 11 from there. But now for 32, it's not constant, because for 32, hash function will give us 2. But at the second index, you can see we have one linked list. So we need to first traverse whole linked list and then find it out that element exists or not. Correct? So that's what with separate chaining, we just increase little bit complexity. Okay, the time complexity little bit increased here. There is another way also, which is called linear probing, which is, though I'm telling you, right, two ways are there. One is this one, separate chaining, and another one is called linear probing. In that way, that is very easy actually. In that way, what we do, guys, when we have a similar structure, 0 1 2 3 4 5 6 7 8 9, and if we have a same input like 11 12 13 22 28, what else, 18 18 and 19, and when we have the same 11 mod 10, it will give us 1, it will go into this position, 11. Correct? Now we'll go for 12. 12 mod 10, it will give us 2. So here will be 12. Correct? Now we will do the 13. It will give us 3. We'll go here, 13. Now for 22, once we got the collision, what we'll do, we will linearly search the next available position. We will be linearly search the next available position, which would be here. So 22 will come here. That's what the linear probe is. It means once we got the collision, just search the linearly wherever the element is exist. Here we are using array. See, no, we are not using anything else here, anything here. Array is already there, right? This is also array, right? Hash table always created with two things. Hash table always created with two things. Here we're using array instead of linking. No. For collision, we are just searching in that array and finding out the next place. We are not creating any new data structure out of it. At that index, we are not creating any new data structure there. We are just looking for next available place. So that's why, because second method name is linear probing. Let me tell you the name. There are names, I will tell you. Yeah, so first one is separate chaining, as you can see, and second one comes under the open addressing, which is linear probing. This one I'm right now talking about, the linear probing. You know, yes, in open addressing, yeah, this is the linear probing. We just need to find out the next place in the linear probing. Correct? Won't it defeat the purpose of hashing, the linear probing? No. Why it will defeat the purpose of that? See, what was the purpose of that? Purpose of that is we need to find the position. So we are looking for linearly the position. If next index is not available, it can also go for the starting one as well. It can also go for the starting one as well. Like you can see, till now, till ninth index, if we do not find any of the element, it can go for 0 as well. And then once we already completed our hash table, we'll say that hash table is full. We cannot store our information. We cannot store any next element here. That's happened here. That's why when we have like a smaller space, when we have a use case or data sets where we have a smaller number of elements, then we go with this way. Otherwise, the globally everywhere, mostly like in a generalized way, separate chaining has been used. These are the other like linear, quadratic, and other. They have been used in different use cases with the different data sets. Okay. So in the linear probing, once we have an element in the, once we see the collision happen, we will be looking for next available space in the table. In that same table, we will be looking for next available space. And wherever we find the next available space, we'll simply put the information there. And this also creates the linear problem also create clustering. Linear prob also create, yeah, we'll say that hash table is full. We have to delete something from there. We can't store next information here because our hash table is full. With this way, we can't store next element here. We'll say that our hash table is full. You just need to increase the size of hash table, or yeah, I think that's the only way. How will it retrieve again from a different location? We will use the same method, right? Once we went for like, see, if we are looking for 22, so first hash function will pass it. In hash function will pass it. Yes, it will check in the 2, and we see that it's not there. So what we will do? We'll increase the index. We'll increase the index. We'll look for next index. We'll see it's not there. We'll look for again. See, so definitely problem is there. Definitely problem is there with the linear probing. Yeah. Yes, it will definitely affect in time. See, in the separate chaining also it was happening, right? It will affect in time. So these are the ways. See, we are not telling you that how to remove it fully. We are not talking about how to remove it. We are talking about how to handle it. So which could be better. So these are different ways to handle these things. And these ways has some advantage, has some disadvantage. Yeah. So see, there are quadratic probing is also there. In the linear probing, there are two more probing is there. Quadratic and double hashing is also there. So let me see, in one places I have written it. Yeah. So linear probing has already explained you. It just increase the size. You can see here the example. Let me increase a little bit size here if I can. I think I can't. Let me 1 minute. Yeah, font is there. Yeah, a font is there. No, size I'm talking bigger. Oh, for bigger it is this. Yeah, okay. Yeah, yeah. So now you can see in the linear prob, one slot to another for free space. So what we do, you can see first we got 55. So 55 mod 10. 1 minute. It is some wrong example. Yeah, just take the 6, 10, right? Both places. Yeah. So 55 mod 10, 5. So in that example, 45 already was there. So what we'll do? We will just increasing plus 1 there in the 55. So we'll get 56. And then we are doing the mod of it. And then you can see full as 66 is already there. Then we are looking for 7. That's what the linear probing. We just look for the next available index. And how we look for? We just do plus 1, plus 1, plus 1, plus 1. And then we got for the in the quadratic probing, we just look, we do I square. Rather than, see, here we were going linearly, like 1, 2, 3. But in the quadratic, we do the 1 square, 2 square, 3 square, 9 square, like that. Like that, we go in the quadratic probing. See, this is a similar way to just look for the next available position. So that's what the quadratic probing. And in the double hashing, the formula is little different. So what they do, h of k plus I multiply by h of k, where I is between 1 and size of table. See why quadratic and double hashing comes into the picture. Let me tell you why quadratic and double hashing comes into the picture. Because with the linear probing, clustering happen. Let me tell you why clustering. What is a clustering here? If we have linear probing here, and if we have 20 elements here, like 10, 11, 12, 13, 14, 15, 16. Because as the linear probing says, if we have some element here, like 27, so next time any element is coming, which is having the 7 as a key, it will be stored here, 37. 47 will be stored here, 57 will be stored here, 67 will be stored here. You can see clustering is happening, which is not good, because as for the best hash table, your keys should be uniquely distributed in whole of hash table. Your key, your information should be uniquely distributed in your hash table. But with the linear probe, it is making a cluster. You can see it is just making, because what linear probing says, wherever you find that key, just go into the next one, next one, next one, next one, next one. And when you reach to till the end, then go for the top one, then go for the top one. So that's why clustering happen. For removing the clustering, they have given these two other way, which is quadratic and this double hashing. Because in the quadratic, you can see you are jumping 4 position. You see, in the quadratic, as I showed you, you are jumping 4 position. You can see 1 square, then 2 square, then 3 square. So you are not jumping 1 position one by one. You are jumping 2 for first time you are jumping 1 position, then 4 position, then 6 position. So that's how the quadratic. And in double hashing, they are saying for the next slot, you need to compute this thing, h of k plus I multiply h of k, like something like this. It will happen like if we look for 22, so for 22 it will be 2. Then they are saying let's start a loop here, and that loop will run from I to table size, which is 20, right? So they are saying 2 plus, right now I value is 1, so 1 multiplied by 2, so it will be 4. Second time it would be 2 plus 2 multiplied by 2, which would be 6. 2 plus 3 multiplied by 2, which would be 8. So they are saying here, now look for these positions. You see, that's what they are saying. So this is not making it, it is like a cluster. They are not making it in a cluster now. With linear probing, it was a cluster. See, Vishal, clustering is a problem because as I was telling you, we should be storing our keys in a uniquely distributed. Like it's not like it's just everything is going into the downside. We have a space on the top side as well, right? Why we are not doing that? Correct. And you see, there is one more problem, in the like if for the 22, see, there is one more problem for 22, like for the second, for 42, we need to traverse everything one by one. We need to traverse one by one, then we'll get the 42. If we are going 52, we again need to traverse one by one. That's again second problem of cluster. We need to traverse one by one to everyone, then to reach to the next place. But if we are using other ways like quad probing or the double hashing, we are jumping little bit extra compared to linear one. Yeah. Linear probing would reduce the efficiency of hashing. See, because right now we are talking about handling the collision. So whenever we are handling the collision, it definitely reduces the efficiency because we got the collision. If there is no collision, we can simply do it in constant time. If there is collision is happening, we are definitely going to reduce the efficiency of hashing. Okay, guys, so these are, I think, 3 to 4 ways which are available right now for handling the collision, guys. And see, you can see they have given the advantage also for the separate chaining, the linked list one. They're saying this is the advantage is average cost of searching the element will be O of n, where n is total number of keys. They are saying it is an advantage, guys. You see, they are telling it is an advantage. In O of n time, we can simply find out the element. If it is in the linked list, we just need to traverse n time in worst scenario. If that linked list has the element at the last, they think this is the advantage. And disadvantage is there is no bound on the size of linked list. Therefore, it might grow out of bound as well. So that because yeah, yes, that's right. Because the linked list, we do not define the size. We do not define the size. So linked list could go out of bound as well. That's totally true. I meant providing just the next place means has to be created could already be occupied, as you said. Yes, yes, it could be occupied. Yes. Let's read the disadvantage of other one, open addressing. So advantage is consume less storage. Yeah, they're saying we are not using linked list. That's why it's consume less storage. Slower than separate chaining. Yes, definitely. More traversal is needed there. That's why it's slower than separate chaining. That's the disadvantage they are telling about the open addressing. Okay. So I think before that, guys, we have just missed the hash table, like hash function. But yeah, before we will jump into the hash function, but let's talk about your queries. Let me go back to the previous and let's see what are the queries you guys have. Okay, till now I think Likhit question I already explained. Quad probe will increase the size unnecessarily. Why do you choose this? It's not increasing the size. Quad probe is giving you the positions, more positions. It is just leaving the middle part. How it is making cluster, already explained it. Group of anything, they're making a group. I can't see why. Okay, already I answered that one. If we top side also want it make cluster, yes, on the top side also it will make cluster. But you know, with the quad probing and open addressing, we are equally going into the each spaces and then putting the information there. So it will reduce little bit cluster. But it will you if you will use the linear probing, then from the top side also it can make the cluster. Yeah, now understood. Okay, guys, I think we have understood this part. Let's also understand the hash functions. There are different type of hash functions also, but the popular one is the one which we are using, which is called the division method, which is called the division method. This is the popular one, and this one we are going to use for our implementation also. When we'll implement, we will also use the division one. But there are multiple ways. You guys just see, nobody is going to ask you, but you guys just understand these things, okay? Just understand these methods as well. I have this one GFG where they are explaining about the hash functions and different hash functions. So let's start with division method. So we already seen example of division method where we'll get the key and mod m. Yes, but important thing I told you, right, that while creating your hash function, you should think about how can you reduce the collision. How can you reduce the collision? So for that, in your division part, your division part, they are saying we should be using m as a prime number that can make sure the keys are more uniformly distributed. Why they are saying prime number? You know that prime number only, what is the property of prime number? Prime whole number only divided by its own number and then divided by 1. Prime number has the property, it can only be divided by his own number or 1. Correct? So that's why if you will use your mod value, right now I'm using 10. So 10 can give you more collision compared to any of prime number. Or there is one more condition. Or you should use a number which is uh, less devising. Less devising. It means the number which give you less division. Like what is the correct word to say? Like 2 is not the ideal number. 2 and less are not the ideal number. They can divide by everything. You can divide 2 and 10 with everything. You will definitely get a lot of collisions there. But if you use a number which divide less, like 93, I think 93 is also prime number. No, 9312. It's not a prime number. But yeah, 93 could be a number which is less divisible in your size of air. Like if you are taking a size of 100, size of like your table size is 100, then you can take you can choose your m as 93 also, which will give you very less collision. And yes, a prime number. 93 is prime. Okay, 93 is prime then. I'm not sure about that. 96 prime or not. Let's see. I think it can be divided by 3 also, right? 93. It's not. Yeah, 9 plus 3 is 12. That's what I'm saying. 12 is divided by 3. So 93 is not the prime number. But 90, I'm saying that 93 is, it could be a number which can give you less divisions. That's what I want to explain you. So these are the two conditions. Yeah, less divisors. Yeah, that's what. Less divisors, which can give you less divisions. That's what I'm going to see. Like 2 or 10 or like 4, 8. You can divide a lot of numbers with them. But if we take little bit bigger number, which has less divisions, it will give you less collisions. So that's what, guys. So that's what the properties they are saying, that it's best suited that M is a prime number, as that can make sure the keys are more uniformly distributed. Then they are given the one example also. So this is our key 1, 2, 3, 4, 5, which we want to store it. And they have taken M as a 95. I think 95, it's a prime number. No, 5 is at the end. How can it be a prime number? But it's still, I think it would be less divisible. So you can see when they had taken the mod, we got the 90 position as a remainder. You know, in the mod, we got the remainder. So 90 is there. 11 is the prime number. Yes, 11 is the prime number. So it's a 0. They are telling the pros also. The method is quite good for any value of M. The division. Oh, yes. One more thing, guys. While creating your hash function, you should always think about one more thing. So first property is that you should get less collision. That should be your, there is no hash function where you will not get collision. There will be definitely some hash function, there will be collision, but you should try to go for lesser. And second one is your hash function computation should also be easy. That's why people use the division method. You can see computation, it's very easy. You just bring the number, divide it. Very less computation. That's why always, because you know, every time you need to do computation, right? When you're trying to find something, you need to do that computation. Whenever you are storing something, you need to do that computation. You need to create every time hash value, right? If you are going to store some information, you need to create the hash value for that. If you are searching for something, you need to create the hash value for that. So that's why your hash function computation should also be less. That's what the two property you need to remember when you're creating any hash function. So your hash function, you see, anyone can create hash functions. You guys can also try to think about it. How can we create a hash function which would give us, and your perfect hash function would be which gives a very less collision, and computation is also easy, not difficult. There are not a lot of steps are there. That's what we will see in the next some other hash methods. Yes, we use real. Yes, we use it in real words. Yes, we use it. Okay, so let's see some other examples also. Let's see what are the advantages and disadvantages here. Yeah, that's what the second thing they are saying. The division method is very fast since it's require only a single division operation. That's what. Now cons is also there. This method leads to poor performance since consecutive keys map to consecutive. This is, they are telling about the collision only. They are telling about the collision because this could give us multiple collisions as well. Sometimes extra care should be taken while choosing the value of M. That's what I already told you. Correct, guys. Now let's talk about the second method. Second method to create our hash function, which is they are saying, which name as mid square method. What we have to do whenever we are taking a key, just square that key, and extract the middle R digits as the hash value, and that value of R can be decided based on the size of table. We will be able to understand with example only. So let's go into example. So this is the key 60 which we want to store. So what is the first step? Square it. The first step is square it. So once we'll square it, we'll get the 3600. Next, extract the middle R digits. Extract the middle R digits as the hash value. And R will be depend on your memory size or your table size. That's what they're saying. R can be decided based on the size of table. So now you can see, suppose the hash table is 100. It means it will has a memory location of 0 to 100. It means always two locations. So that's why you need two digits. If you have 1000, it means you can have three positions. You have to extract middle three digits. So that's what you can see. Hash of 60 would be 60 because once you squared it, middle two digits are 6 and 0. So that's why the answer for this technique is 60. Understood mid square method, guys? It was easy, right? Square it, take the middle digits, and that middle, how many digits you need to take? It depends on your table size. But there is one problem in this method as well. They will read in the pros. So now let's talk about the advantages. So advantage of this method is good as most or all digits or key value contributing to the result. This is because all digits in the key contribute generating the middle digits also. So they are saying like this the advantage is here like whole key is has been used for contributing to generating the hash value. In some places it could be whole key is not contributing. That's why they're saying it's good actually. The advantage they are selling that advantage is it is telling it as an advantage that whole key we are using it while creating a hash value. Let's see next one. The result is not dominated by distribution of top digits or bottom digits. Oh, okay. You know, in the division method, you know, in the division method, your answer of hash value is always dominated by last values because you know we are calculating the mod. In the mod, always your answer will be, you know, dominated with your mod value because your answer should be between those mod value. But here it's not the case. That's what they are telling it. Here all the keys they are saying all the digits of that number is contributing, and on all and also our result is not dominated by some top digits or bottom digits of the original key value. That's what they are selling. That's what the advantage they are selling. And the problem is here the size of key is one of the limitation of this method because if you have a like number 6 million and then you are squaring it, so it will become like more bigger, and then you are finding out the digits between them. You can see how much computation you have to do. First you have to square it, store that number in somewhere, then you need to go into the middle position, you need to find it. So that's a cons here. That's the disadvantage here. Another disadvantage is that there will be collision. Collision will everywhere happen. What is it? I hope you understood the mid one, mid square one. Correct, guys? Let's move. Let's see two more. Two more are there. So third one is digit folding method. Digit folding method. So what is happening here? There are also two steps. Divide the key value k into number of parts k1, k2, k3, kn, where each part has the same number of digits except for the last part that can have lesser digits than the other part. Okay, add the individual part, the hash values obtained by ignoring the last carry if any. Okay, let's see. So this is our example 1 2 3 4 5. They are saying divide this key into each part with the same number of digits. Divide this key with the same number of digits. So that's what we have divided our key 1 2 3 5 into k1, k2 and k3 with same number of digits except the last one. You can see they're saying except for the last part that can have lesser digits than the other parts. So you can see in the odd scenario, see in the odd scenario always if your number is odd, then it always be last digit will be alone. But if your number is even, this scenario will not happen. And then once you got these numbers, just add them. You will get your hash value. You will get your hash value. That's what the answer is here. They're not telling any advantages and disadvantages here. Number of digit in each part varies depending on the size of hash table. Suppose for example, the size of hash table is 100, then each part must have two digits except for the last part. Oh, they're also telling guys here, same like the mid square method, the value of r. They're also telling here, how will you decide how many partition you have to do? How many digits in your partition should be there. They are telling that's again, it depends on your size of hash table. If your size of hash table is like 100, it means you can take 2 digits. You can divide it into 2 1. And if you're 1000, you can divide it into 3 1. That's what they are telling here. Number of digits in each part varies depending upon the size of hash table. So that's what the way is here. You have to divide it, and how you have to divide it. You have to divide it based on your size of hash table. That's the third one, guys. It's little bit similar to the previous one, mid square one. Little bit similar. Okay. let's look into the last one, the multiplication method. Okay, there are 5 steps. Let's see what are these 5 steps. Choose a constant value a such that it is between 0 to 1. Okay, you have to first choose a value between 0 to 1. These all are computation steps of hash function, guys. So first step is you have to choose one random value between 0 to 1. Okay, next, what is that? Multiply the key value with a. So whatever value you have choose, multiply it with the key. Like you have key 28. So first multiply 28 multiply by 0.1 if you are choosing a value of a as 0.1. Then what is that next? Extract the fractional part of it. So see, guys, once you will multiply 0.1 with the 28, so it will become 28.01, right? If you multiply 28, do it. It will become 2.8. Sorry, guys. I am also confused. 1 minute. Let me tell you. 28 multiplied by 2.1. It will become 2.8. So they are saying fetch the fractional part. It means fetch the 8. Understood, guys? Understood, guys? Fetch the fractional part. Everyone understood? They are saying fetch the fractional part. So fractional part is 28 multiplied by 0.1. Fetch the fractional part, which is 8. That's the third step. Let's see what is next step. Extract the fractional part of Ka. Multiply the result of above step. Multiply the result of above step by the size of hash table. So now the next thing is whatever 8 is coming, you have to multiply it with the size of hash table. And then I think the resulting hash value is obtained by taking the floor of. Again, we have to take the floor of step 4. I think a lot of steps are there. So let's see, guys, with the examples, let's understand better. So I think there are 3 things which we need to consider here. One is the a, variable a. Second is the size of hash table m, and k is our key which we want to hash it. So now k is 1 2 3 4 5. They have taken a value of a which has to be between 0 to 1 as this one, 0.357840. Okay, m is 100. M is 100. Now let's see. So our key is 1 2 3 4 5. Okay, first they have multiplied it. Okay, after multiplying it, what they're doing, they are okay, after multiplying it, we are okay, so mod 1, mod 1 is giving us the fractional value. You know, guys, mod 1 will give us the fractional value which is 0.5348. You can see that's why 0.5348 fractional part. What was the first step? Choose the value, already chosen. What was the second step? Multiply the key value with a. So this is happening the multiplication. After that, extract the fractional part. How they are extracting it? With mod 1, because mod 1 will give us the all the decimal parts, all the digits after the decimal. Or you can directly take the floor as well. And now 0.5348, 100. Now you multiply it with the size. So 53.48, and now you are taking the floor value of it. So this is our key, 53. What is the advantage here? So now advantage is here. It can work with any value between 0 and 1. Although there are some values that tend to give better results than the rest. They're saying that we can choose any value between 0 to 1, and that is a benefit here. Okay. Not sure about it, but yes, I think we will take more examples. Then I think we might get some ideas here. Why this is an advantage. Let's read about the disadvantage here. The multiplication method is generally suitable when the table size is power of 2. Then the whole process of computing the index by the key using multiplication hashing is very fast. Okay, they're saying the value of m, the table size, we should be choosing it the power of 2. Then I think they are saying our hashing could be a little bit faster. So I think this I think pros and cons we can only understand with more examples here, guys. We'll take some more examples, then we will understand these things. But yeah, I just want to show you these are some of the like different methods which we had here, and most of the places we are going to use the division method, guys. And for the collision resolution, we are going to use the chaining one. Okay. So I think that's all from today's class, guys. No. These are not. See, in the JavaScript, guys. Let me now tell you truly. In JavaScript, for hashing, we simply have object and map. We simply have object and map. So no need to implement hash table data structure there. They have already internally implemented it and provided in the way of object and map. We already had it. We're already using it in many places. Okay. Now in interviews, whenever somebody is in asking in interviews, they are simply asking you to use that hash map or object in the problems. See, every time we are using any data structure like linked list, binary tree, we are using it to solving problems, right? Correct. Like in the top tree, in the top view of tree, you remember we were using the map. In top view of the tree, we were using the map. You guys remember that? Yeah, that's the hash table. That's the hash table only. In JavaScript, hash table is object and map. So I don't think anyone is going to ask these things. But yes, if you're going to give any like specific interviews like cyber securities, specific interviews like which are going to be cyber security based, or like the security specific interviews, they might ask you these methods there, or the collision resolution methods they could ask there. But till now, I'm telling you guys, I have not seen anywhere they're asking me in any interviews to implement all of those things. Yeah, we are using it. You know that object and map we are using in a lot of problems. That we only need to remember. And I think in next class we are going to solve some problems as well. There we will see how to use them. But yes, we are just trying to know here how these things are internally working, how JavaScript object, how JavaScript maps internally work. So it internally work with the help of these hashing, with these hashing strategies, or these hash functions have been used here. Okay, guys, are we good? Are we good, guys? So we can now meet into the next class, and we can go for the next slides here, which is I think implementation of hash table, where we will be using like I told you, right? We will be using one hash function, and then we will be using array, right? We will be using arrays. Now see, earlier in this further slide, they are telling about the map and objects. We'll talk about later. And then once we have created our hash map, we will now then talk about one of the way to handle the collision as well. That will be separate with this separate chaining way. And then we'll see some of the problems based on the hashing. Okay, guys. So let's meet it tomorrow. Whoever find it interesting till now, they should definitely join tomorrow's class, which is going to happen on 10 o'clock, I think. Okay, guys. So I'm hoping everyone found it interesting. So did you guys find this little bit interesting? See, it's not difficult. It's just some logical part. I already told you while starting this topic, it was little bit theoretically and conceptual. And now we are going to talk about a little bit problematic here. Second question. Yes, second question was very interesting. Yes. Second question was very interesting. I want you guys to practice it. That question has been asked in bigger MNCs. Like MNCs, I'm saying bigger product-based companies. So definitely practice it. That question was interesting. And tomorrow, once we completed this hash table, I will try to solve some problems. Like see, the problems which we solve with the hash map, it's like find out the duplicate letters. These are the problem which we use this object and hash map. So we'll talk about them. We'll talk about them in next class. Okay, guys. So let's wrap it. Let's go for sleep, and then come back in next class, which will happen on tomorrow morning. Okay. Good night, guys. We'll talk tomorrow. Bye bye.